When you look up at the night sky, it feels wide and quiet, like a deep lake at dawn. Our sun is just one small light. Beyond it, space keeps going, calm and cold. Somewhere out there is the next shore, another star with worlds of its own. Could we ever reach it? Our rockets are brave, but space is bigger than every map we have. Still, people dream. They imagine sails that ride on light, steady engines that glow for years, even long sleep for long trips. In this episode, we follow that dream carefully, one simple step at a time. If this gentle journey speaks to you, tap like and subscribe so you don't miss the next chapter. Settle in, and we begin. Beyond Neptune, past the dim ring of icy bodies called the Kuiper Belt, space grows quieter and thinner. The sun's pull weakens, and the tug of other stars begins to matter. This edge is not a wall. It is a fading glow we have mapped with instruments and math, not with hands. A simple question lives there. Will we stay close to our star, or slip beyond this reach and keep going through the dark? People have asked that kind of question since long before telescopes. Without rockets or equations, ancient skywatchers read the sky with stories and steady observation. They traced patterns among bright points and named them hunters, rivers, animals, gods. These shapes were not only tales, they were calendars for farmers and guides for sailors. The night sky became a clock that did not fail, a map that did not burn. Inside those stories, a seed of science began to grow. Some thinkers proposed that the stars might be suns very far away, and that other worlds might circle them. If there are many stars, they asked, why not many worlds? The idea did not push Earth into the background. It placed Earth inside a wider home. Curiosity drives that widening. It is the human habit of reaching for what is just beyond reach, naming it, and checking if the name fits. The same drive once carried people over mountain passes and across dry deserts with simple tools and careful plans. Horizons did not stop them. Horizons drew them forward. When the first bands of humans left Africa, they walked into unknown lands and weather, found new foods and new dangers, and made new ways to live. Today, the horizon sits where the sun's light thins into interstellar space. The pull on the mind feels the same as it did at a shoreline long ago. The night sky can make a person feel small. It can also calm the mind. There is comfort in the steady rise and set of stars, the slow paths of planets, the patience of light that has crossed great distance to reach our eyes. Many people hold both feelings at once, small in body, wide in thought. The two do not cancel each other. A person can live a brief life and still ask long questions. A person can stand on Earth and still imagine a path to another sun. The wish to go outward also has a practical side. Life on Earth is strong, but not guaranteed. The planet has faced hard shifts and sudden shocks. About 65 million years ago, an asteroid ended the long age of the dinosaurs. Volcanoes have darkened skies. Ice has advanced and retreated. We also know that human choices can strain the systems that keep us alive. For some scientists and planners, reaching other worlds is part of a safety plan for life itself. If life spreads, it can endure even when one place is hurt. This is not a plan to abandon Earth. It is a way to protect what began here. Adventure adds quiet heat to that plan. People have crossed open oceans in small boats, knowing the first days would be hard and the next days might be harder. Climbers have stood on thin ridges with cold air and clear views. The risk was real. and so was the reward. To learn what a person can do, to see what was hidden, to turn a blank line on a map into a known path. Space is the largest version of that habit. It is not kind or cruel. It is simply there, open, silent, steady. The draw is not only danger, it is the promise of new ground, even if that ground is dust, ice, or a metal floor inside a small, pressurized room. In recent centuries, our tools turned longing into knowledge. About 400 years ago, a simple tube of glass revealed moons circling Jupiter. That picture changed our place. Earth was not the center of all things. It was one body in a system, and that system was one among many. Later, better instruments showed that our galaxy holds hundreds of billions of stars, and beyond it lie other galaxies without count. We began to find planets around distant suns. Some are big and hot, some are small and cold. A few sit in zones where liquid water might last on a surface. Space telescopes like Hubble and James Webb have shown us far-off galaxies and the faint fingerprints of elements in distant worlds. Each discovery made us feel less alone and more precise in our questions. In the 20th century, the line between looking and going blurred. A single orbit by a single person proved that a human body can live, for a time, beyond the air. A few years later, boots pressed into the moon's gray dust. That step did not bring the stars closer, but it reset the scale of what felt possible. The moon is our near neighbor, yet it is not Earth, and humans stood there. That fact became a marker for what careful work, clear goals, and patient engineering can do. The pull of the stars is not only a record of missions and dates, it shapes how we think and create. It appears in stories, songs, and images shared at kitchen tables and across screens. A child drawing a rocket is taking part in an old pattern. Imagine a place first, then ask how to reach it. Most people will never leave the atmosphere. The shared picture still matters. It gives meaning to slow, exact work done in labs and control rooms. It says the effort is about more than machines. It is about keeping a promise to the next hands and the next minds. Travel beyond our system would carry more than bodies. It would carry languages, recipes, tools, and quiet ways of care. A small station on Mars or a ship bound for the outer dark would hold birthdays, jokes, old lullabies, and new holidays tied to new skies. Life spreads not only by cells, it spreads by culture. It brings warmth to cold places and turns a habitat into a home. The hard part is distance. Even the nearest star beyond the sun sits far beyond normal sense. With engines we have now, a crewed trip would last far longer than any single human life, and longer than many lines of history. The numbers can feel heavy if they stand alone. Used well, they set the size of the task. They tell us that speed by itself will not be enough. We will need engines that run for years without fail, habitats that repair themselves, and good ways to keep minds and bodies healthy when the view outside changes only slowly. Set against those demands is a record of steady progress. Fire and cloth became steel and code. Looking became leaving. We learned to recycle air and water, to shield against radiation, to land with care, and to send robots where bodies could not yet go. None of this erases the gap between stars. It does show that the path ahead is not blank. It carries marks, and those marks point in a clear direction. From orbit, astronauts describe the overview effect, a shift that comes from seeing Earth whole. Continents turn into color and shape. Borders fall away. Storms and forests share one thin shell of air. The sight is not a lecture. It is an experience that becomes a lesson later. Many who feel it say a simple truth: leaving home can teach what home means. The drive to explore and the duty to care for Earth can live side by side. They are partners. To keep this world healthy is to keep the launch pad strong. To go outward is to learn how rare and bright this place is, and to carry that knowledge into the quiet beyond. The solar system is a vast, orderly family bound by gravity, and its scale sits far beyond daily sense. Even the first step, the stretch from Earth to the Sun, is about 1 astronomical unit, the average Earth-Sun distance. That single stride is already huge, yet it is only the opening measure of a much larger score. Each planet moves at its own pace along a stable path, set by the Sun's pull and the planet's mass. Mercury loops around in about 88 days. Venus takes about 225. Earth's path sets our year. Mars needs almost 2 Earth years. Farther out, the clock's slow. The giant worlds circle more slowly still, and Neptune takes well over a century to complete a single lap. Distance grows quickly as you travel outward. Jupiter orbits about 5 times farther from the Sun than Earth does. Saturn sits roughly twice as far again. Uranus is near 20 Earth-Sun distances, and Neptune near 30. Past Neptune lies the Kuiper Belt, a broad ring of icy worlds and dwarf planets that stretches for tens of these Earth-Sun steps. Numbers can feel abstract, but the pattern is plain. Space widens fast, and the gaps between worlds expand much more rapidly than the worlds themselves grow. Compared with those gaps, the planets are small. Earth is a compact marble next to Jupiter's wide globe, which is more than 10 times Earth's width. Saturn follows close behind. Uranus and Neptune are smaller than the 2 giants, but still dwarf our home. Against the emptiness between orbits, even these large planets are like tiny beads on a very long wire. Moons add another layer of scale. Our moon sits about 30 Earths away, if you lined Earths up side by side. Around the giant planets, some moons move at distances greater than 1,000,000 kilometers from their worlds. Each system is its own neighborhood, with smaller paths nested inside larger ones. The Sun dominates this whole structure. Its diameter is about 1.4 million kilometers, and its gravity shapes every orbit from Mercury to the faint edge of the heliosphere, the bubble where the solar wind finally yields to the thin wind from other stars. Far beyond, a distant shell called the Oort cloud may hold icy bodies that drift so far from the Sun that it looks like just another star. Even there, gravity still whispers, though it grows weaker with distance, allowing loose, slow orbits that take ages to complete. Between the orbits, most of what exists is space itself. These broad, almost empty reaches are not mere gaps. They are the stage where gravity does its work. In that stage, you find belts and families. Between Mars and Jupiter lies the asteroid belt, a wide span filled with rock and metal left over from the system's early days. Sizes range from dust to the dwarf planet Ceres, nearly 1,000 kilometers across. The belt is not a packed field of boulders. It is mostly open, with small bodies moving along careful tracks at high speeds, their paths shaped by the Sun and the pull of Jupiter. Comets give a different view of the system's size. Many start in the Kuiper Belt or the Oort cloud and follow long, stretched-out orbits. As they fall inward, sunlight warms their surfaces and streams gas and dust away, tracing their routes with glowing tails. Some take decades to return, others take centuries or longer. Halley's Comet, the classic visitor, completes one long loop about every 76 years, diving toward the inner system and then fading back into the dark. These long paths link the near and the far, turning the solar system into a single, extended track rather than a set of isolated stops. Light itself reminds us how large this family is. Even at the fastest speed nature allows, sunlight needs about 8 minutes to cross the Earth-Sun gap. Reaching the outer planets takes much longer. The trip to Neptune is measured in hours, not minutes. When light needs hours to go from one place to another, you know the distances are beyond everyday scale. Spacecraft feel this as well. Signals sent to and from deep space missions arrive with a built-in delay, and navigation is planned with that delay in mind. The Voyager probes, launched in 1977, make the point in a human time frame. They crossed the orbits of the giant planets years after launch, then kept going, driven by their early push and guided by tiny course corrections. After more than 4 decades, they passed through the outer boundary where the sun's wind gives way to the interstellar medium. They are still moving, still sending back faint data. Their long journeys show that leaving the sun's protective bubble is possible, but it also takes patience, engineering that lasts, and respect for the distance. Beyond Neptune, a wide population of trans-Neptunian objects fills the cold. Some, like Eris and Haumea, are dwarf planets with stretched or tilted orbits. Farther out, rare bodies trace extreme paths that take thousands of years to complete a single circuit. Out there, sunlight is weak and slow to warm. On objects like Sedna, a day's worth of light on Earth would take nearly a day to arrive from the edge. These remote worlds mark the system's reach in a way no single planet can, showing that the sun's family extends deep into the dark. All of this structure came from simple beginnings. Long ago, a cloud of gas and dust collapsed under its own gravity. The center grew hot and bright and became the Sunday. Around it, a thin disk of material clumped together. Small grains became rocks, rocks became mountain-sized bodies, and those merged into planets. Collisions shook the layout. Some worlds migrated, others were broken and rebuilt. The gaps and belts we see today record those early events. The distances and patterns are fossils of formation, preserved in motion rather than stone. As tools improve, details sharpen. Telescopes map storm bands on giant planets, read the thin signatures of chemicals in exoplanet atmospheres, and image ring systems and surface ice in fine relief. Computer models test ways that planets can shift and settle, matching simulations to what we observe. Even with better instruments, the mind still strains to hold the full span at once. Scale is the lesson that keeps returning. It shapes planning for missions, too. A well-timed trip to Mars can take most of a year. Reaching Jupiter often takes more than 6. Neptune sits beyond a dozen years of careful flight. On these paths, fuel, timing, and tiny course changes matter more than raw speed. Seeing the system as a whole also clarifies the sun's role. It is one star among many in the galaxy, yet it is the anchor and furnace of this family. Its gravity sets the dance. Its light drives the weather and seasons on Earth and powers winds and chemistry across other worlds. In the middle of so much emptiness, the sun supplies order and energy, tying the near and the far into one connected space. Distances in the solar system are vast and always changing. Planetary paths are not perfect circles but ellipses, so the gap to the sun grows and shrinks through the year. Earth comes closest in early January at about 147 million kilometers and farthest in early July at roughly 152 million kilometers. Every planet follows its own oval, set by gravity and motion, turning the system into a shifting pattern rather than a fixed machine. Size and distance work together to create rare sights. From Earth, the sun is about 400 times farther away than the moon and about 400 times wider, so their disks can match almost perfectly. That near balance gives us total solar eclipses when the geometry is exact. We also see transits, tiny dots of Mercury or Venus crossing the sun, and slow alignments that take years to arrange. These events show that great gaps do not prevent clean, precise lines in the sky. Scale in space is also scale in time. Worlds spin at different rates. Jupiter turns in just under 10 hours, while Neptune needs more than 16. Orbits take months, years, and decades. Tiny pulls between planets add up over millions of years. Motions we trust to be steady are part of much longer stories than a human life. Small bodies keep the picture lively. Meteoroids, comets, and asteroids race along stretched paths at high speed. Sometimes they meet a planet. In 2013, the Chelyabinsk meteor entered Earth's air at about 19 kilometers per second and broke apart high above the ground. It was a clear reminder that even modest rocks carry great energy after crossing long distances and falling into a deep gravity well. This scale reshapes how we think about travel. Going from one world to another means planning for distance, time, and fuel together. A spacecraft must aim not at where a planet is now, but where it will be months or years from now. Small course changes early can save large ones later. Long cruises demand steady power, robust navigation, and systems that can care for themselves far from help. Abstract gaps become practical routes when turned into launch windows, transfer arcs, and quiet mid-course checks. Understanding the system's size also sharpens our sense of Earth. Among the known planets, Earth holds liquid water, a protective atmosphere, and a stable partner in the moon. In a family marked by extremes of heat, cold, and radiation, our world sits in a narrow band that allows life to endure. The wider view makes that placement feel both fragile and fortunate. The outer reaches extend the sun's influence into near interstellar space. Far beyond the planets, a deep reservoir called the Oort cloud likely holds icy bodies on orbits measured in tens of thousands of astronomical units and in millions of years. These objects spend nearly all their time in darkness, nudged only by faint pulls. When a few drift inward, they brighten as comets, cross the inner system once or a handful of times, and then fade back to the cold. Exploration keeps filling in detail. New Horizons, launched in 2006, reached Pluto in 2015 after a 9-year flight and revealed mountains of nitrogen ice, smooth plains, and a thin, active atmosphere under weak sunlight. Working that far out means colder temperatures, slower solar power, and long communication delays. Signals take hours to go and return, so the spacecraft must handle many tasks on its own. Each mission shows that distance can be managed with careful design and patient operations. Future steps will stretch that model. Journeys beyond Mars or outposts on moons like Europa or Titan ask us to plan for years in transit and habitats that work in deep cold with little light. Life support must recycle nearly everything. Propulsion must be efficient for the long haul. Crews must stay healthy in body and mind when resupply is rare and help is far away. In this setting, local can mean millions or billions of kilometers, and soon may point to a narrow launch window that returns only after seasons have passed. Close to home work still trains the basics. Missions with the moon, only about 400,000 kilometers away, teach timing, navigation, communications, and surface operations. Understanding its pull and period scales up to Mars transfers, to visits to the giant planet's moons, and to trajectories that move from bright sunlight into deep shadow and back. While probes bring back images and samples, telescopes measure from afar. Radar ranging fixes distances to nearby worlds. Parallax uses Earth's orbit as a giant ruler to read tiny shifts against the background stars. Telemetry from spacecraft tracks speed and position with high precision. Astronomers turn big spaces into workable units, astronomical units, light minutes, and kilometers, so the system becomes a grid that can be analyzed, understood, and navigated. Even the empty lanes matter. Interplanetary space holds dust, charged particles, and cosmic rays. The solar wind flows outward. Magnetic fields twist and bend. Radiation accumulates over time. These faint effects shape shields, electronics, and health plans for deep space flight. They also show how the sun interacts with its surroundings and how that conversation changes with distance. Minor worlds add structure at every scale. Dwarf planets, asteroids, and comets range from a few kilometers to more than 2,000 across. Each follows a path set by gravity. Together they form belts, rings, families, and clouds that give the solar system texture. Fine details fill vast emptiness, turning open space into a patterned whole. Under all of this is a clear framework. Gravity links mass and distance. Motion follows steady rules. Small nudges can lead to large changes over long spans. The math turns the immense into the predictable, showing how a system this large can stay stable and still remain alive with change, and how careful measure can turn hard to imagine scale into space we can plan, cross, and learn from. Stars look close because they shine as tiny points, but even the nearest ones sit at distances far beyond daily sense. The closest system beyond our sun, Alpha Centauri, is over 4 light-years away. A light-year is not a measure of time. It is the distance light travels in 1 year. Light moves almost 300,000 kilometers each second, so a single light-year adds up to a number so large it is easier to treat it as a unit of its own. The glow you see from Alpha Centauri tonight left those stars more than 4 years ago and crossed empty space the whole time to reach your eyes. Proxima Centauri, a small red star in that same system, is a little closer than its brighter companions, but it is still more than 4 light-years away. If a probe moved as fast as Voyager, one about 17 kilometers per second, it would need on the order of 70,000 years to arrive. That span is longer than written history. Civilizations would rise and fall while the spacecraft continued on, quietly, through the dark. The next bright neighbor, Barnard's star, sits roughly 6 light-years away, and at current speeds, the trip would stretch beyond 100,000 years. Even inside our own galaxy, stars are separated by deep, mostly empty stretches. The Milky Way is about 100,000 light-years across, yet most of that width is thin gas and dust. The stars are like lighthouses, far apart on a dark sea. Compared with the Moon or Mars, the scale jump to the nearest stars is hard to bridge. The Moon is just days away by rocket. Mars, at its best window, can be reached in under a year. A star like Alpha Centauri would take decades even for a ship traveling at 1/10 of light speed, which is far faster than anything humanity has flown. Reaching and holding such a speed would demand engines well beyond chemical rockets, steady power for years, strong shielding against radiation between the stars, and a way to slow down safely at the end. Ideas exist: nuclear propulsion, light sails pushed by lasers, even antimatter engines in theory, but None has yet moved from concept to working, crew-ready hardware. Distance in space is also distance in time. The starlight we see is old light. Photons from Proxima Centauri are more than 4 years old when they meet a telescope on Earth. Light from stars tens or hundreds of light years away began its trip when human lives and languages were different than they are now. For stars thousands of light years away, the light left long before any known city was built. Looking outward is also looking backward. In that sense, the night sky is a time machine that shows how things were, not how they are, this instant. Energy sets the other limit. To push a craft to a large fraction of light speed takes enormous energy, then more energy again to slow down. Carrying all of that as fuel is heavy and impractical. Gathering it along the way is hard in a region with almost nothing to gather. The math of momentum and mass insists on careful trade-offs. Lighter ships go faster. Heavier shields protect better. Long trips need power that does not run out. Even for robotic probes, these trade-offs are tight. For people, add food, air, water, medical care, and a place that keeps minds healthy as years pass in a small volume. The gap also changes how communication works. Signals move at the speed of light, so a message to Alpha Centauri would take more than 4 years to arrive, and a reply would take just as long to return. No real-time calls, no live guidance from Earth. A distant outpost would need to make its own decisions and live with long silences. This delay would shape how communities govern, plan, and solve problems. Time becomes as much a barrier as distance. Learning about nearby stars relies on steady observation. Telescopes on Earth and in orbit measure tiny wobbles in a star's motion, small dips in brightness, and faint colors in starlight that has passed through a planet's air. These methods reveal worlds we cannot visit yet. Proxima Centauri hosts at least one planet in its habitable zone, the region around a star where liquid water could exist on a surface. The planet is still only a point of inference for us. A direct visit with current speeds would take tens of thousands of years. So for now, we read its clues from far away. Comparisons help fix the scale. The sun's influence reaches well past the planets. The boundary where the solar wind gives way to the thin gas between stars lies far beyond Neptune. Even if you mark the outer edge as roughly a light day from the sun, the nearest star is still thousands of times farther. The space between stars is not empty in a strict sense. There is thin gas, dust, magnetic fields, and cosmic rays, but it is empty enough that a ship could travel for months without meeting a grain of dust larger than a speck. Dreams of interstellar flight then become plans for endurance. One path imagines very fast, very light probes pushed by powerful laser beams, a sail catching light instead of wind. Another path imagines slow, durable craft with life support that recycles almost everything, accepting journeys that last longer than a single human life. Some designs consider crews who sleep for long periods, if safe hibernation for people ever becomes possible. Others imagine multi-generation ships where children and grandchildren would be the ones to arrive. Each vision tries to balance speed, safety, energy, and time. Closer stars in our neighborhood remind us that even nearby can mean far. Sirius is more than 8 light years away. Epsilon Eridani is around 10.5. Their brightness at night is a matter of both power and distance. They pour out huge amounts of energy, but only a thin fraction reaches Earth after crossing trillions of kilometers. The beam that touches your eye began its trip years ago. In that sense, the stars speak in delayed messages, and patience is built into the way we learn from them. Physics sets clear boundaries. Nothing we know can outrun light. As speeds climb toward that limit, strange effects appear. Time for the travelers would pass more slowly than for people on Earth. For a ship moving at a high fraction of light speed, the crew's clock would tick differently. A journey that took decades by Earth's measure could feel shorter on board. That helps the travelers, but not those waiting at home. Technology must respect these rules. Engineering works within them rather than wishing them away. These distances also shape how we think about purpose. A mission that takes decades or centuries asks for plans that outlast leaders, budgets, and trends. It asks what we owe to future people who will finish what we start. It asks how to build machines that can be repaired by those future hands, or that can repair themselves. It asks how to send knowledge forward so nothing critical is lost in the long dark between stars. Even with these hurdles, study of the near stars keeps moving. Better instruments sharpen our maps of their positions and motions. Improved detectors catch smaller dips in starlight, hinting at smaller worlds. Long projects track the subtle push and pull of gravity across years. Each piece of data narrows the unknowns and turns vague ideas into numbers that can be tested. The scale remains huge. The path remains hard. Yet step by steady step, the nearest lights become less abstract. They are not just points in the dark. They are real places with weather, gravity, and years of their own, waiting across a distance that we can now describe with care, even if we are not ready to cross it yet. Astronomers keep looking to the nearest stars for signs of other worlds. Around Proxima Centauri, a small red sun just beyond our own system, they have found Proxima b, a rocky planet that sits where liquid water could be possible. It has become a clear target for our hopes. Yet sending even a tiny probe there is hard in ways that touch every part of engineering and time. With the fastest ideas on paper, the flight would still take decades. In cosmic terms, that is close. In human terms, it stretches across careers and generations. Each new finding sharpens the picture and also reminds us how wide the space is between here and there. These neighbors teach humility. They show how small we are and how patient we must be. They make clear that our current rockets are tools for a solar system, not yet for the stars. They ask for courage too, the kind that keeps a project alive long after the first spark of excitement fades. Reaching another sun is not a quick goal. It is a line of work that passes from one set of hands to the next. Distance shapes how we explore today. Robotic missions to the outer planets act as rehearsals for deep space. Long cruise times, faint sunlight, tight power budgets, careful navigation, and the need for spacecraft that can solve problems on their own. From Earth and orbit, telescopes extend our reach. Spectroscopy splits starlight into colors to reveal the chemicals in a star or in a planet's thin air. Astrometry tracks tiny wobbles in a star's position to hint at a world circling it. Direct imaging blocks a star's glare, so a dim planet can be seen beside it. Each method gives a different piece of the puzzle. Each successful measurement is a small win against distance. The practical response to scale is planning. Knowing how far a target is helps set what kind of ship is possible, what power it needs, and how long a crew or an automated probe must remain healthy and steady. Calculations turn dreams into mass, thrust, heat, and timeline. Images from telescopes turn guesses into maps. Concepts for propulsion become trade-offs we can test. Light sails pushed by lasers, nuclear systems that burn for years, new engines that sip, fuel, and still give steady push. None of this makes the gap small. It does make it concrete. In the night sky, the nearest stars are more than points. Alpha Centauri, Barnard's Star, Sirius, Epsilon, Eridani, names we can say, and places we can measure. They are too far for people to reach with present craft, but close enough to study in detail. That mix, far to travel, near to understand, defines our current moment. It forces respect for scale while keeping hope active. If leaving the solar system ever becomes real for humans, these stars will be first on the list. The numbers behind that idea are sober: light years of distance, journeys that last decades or longer, energy needs far beyond chemical fuel, radiation to block, life support that must recycle almost everything, minds and bodies that must stay healthy in small rooms over long spans. It is not only a question of speed, it is survival, maintenance, and trust over time. Because signals move at light speed and no faster, distance also slows conversation. A message to a nearby star takes years to arrive, and a reply takes years to return. Any outpost would operate without real-time help from Earth. This delay pushes exploration toward autonomy. Ships and settlements that diagnose, repair, and decide with little guidance. Governance, science, and everyday life would adapt to long silence between messages. Even with those limits, the search keeps paying off. Better instruments find smaller and cooler planets. Longer surveys see how orbits change and how stars flare. New methods tease out the faint fingerprints of water vapor or carbon dioxide in a distant atmosphere. The picture grows finer grain by grain. The work is slow, but not still. The meaning of these distances is not only technical, they frame why we value Earth and why we might travel at all. A star 4 light years away is a hard target. It is also a clear mirror. It shows what it would take to keep a community alive far from home and asks what we would bring besides tools, language, music, ways of care. Thinking at this scale bends our habits toward long projects and shared knowledge that lasts. The nearest lights also set a boundary between the possible now and the possible later. Today, telescopes and probes, careful maps, patient statistics. Tomorrow, faster sails, long life reactors, better shields, closed loop habitats. Farther out, crews who sleep safely for months, or ships that cross the gaps slowly while generations learn and teach aboard. Each step depends on the last one working well and being handed forward intact. Knowledge of these stars anchors our sense of place. It tells us our biggest plans are small compared with the galaxy and still worth making. It reminds us that limits of speed, of energy, of biology are not walls so much as rules we must design within. Alpha Centauri and Proxima Centauri are close enough to set goals and far enough to demand our best. Barnard's Star, Sirius, and Epsilon Eridani extend that lesson in all directions. What the distances finally give us is a clear test. Can we build machines that run for decades without failing? Can we protect fragile bodies from deep space radiation? Can we design systems that close the loop on air, water, and waste? Can we keep purpose strong when progress is measured in years? The stars will not change to make this easier. Their light will keep arriving on its own schedule, a few years late, steady and quiet, until a ship leaves for one of them. They set the scale for everything we try. They mark the edge of the map we can touch, and they keep our curiosity pointed outward. Step by measured step through data, through design, through small flights that last a little longer each time, the first destinations beyond the sun move from poetry to plan, For a long time, people looked up, told stories, and pictured voyages across the sky. Those early tales had no engines, only wonder. As science grew, that wonder took on structure. In the 1800s, writers began to sketch trips beyond Earth with the tools they knew. Jules Verne imagined a shot to the moon in 1865. H.G. Wells turned the view around in 1898 and asked what it would mean if beings came here from another world. Fiction did not build hardware, but it trained the mind to ask practical questions about distance, speed, and what a ship would need. In the early 1900s, those questions found math. Konstantin Tsiolkovsky, working in Russia, wrote down how a rocket's speed depends on its fuel and exhaust, the simple rule behind all spaceflight. He thought first about orbit and the planets, but also pictured sails that ride sunlight and slow, self-contained ships where families might live for generations. The point was clear. Space travel could be reasoned about, not just dreamed. Hermann Oberth in Germany picked up the same thread. His 1923 work explained how rockets could take people between worlds and suggested that nuclear energy might one day power deep space craft. Ideas like these inspired young engineers who later shaped real programs. The interwar years mixed careful calculations with bold sketches, building a bridge from pages to plans. In the United States, Robert Goddard tested liquid fuel rockets through the 1,930 seconds and 1,940 seconds. Liquid propellants offered control and power that solid fuel could not. Some mocked his goals at the time, yet his flights proved that guidance, throttling, and stage descent were possible. Those small launches were the first practical steps toward any future mission that might try the gap between stars. After the war, rocketry matured fast. Long-range missiles showed steady control over great distances, and some of the people who built them turned to space. By the 1,950 seconds and 1,960 seconds, papers began to treat interstellar flight as a physics problem. Chemical fuel would not be enough. Concepts appeared for high-efficiency propulsion, fusion systems that burn light atoms, nuclear pulse designs that push a craft with a series of small blasts, and the Bussard Ramjet 1960, which imagined scooping thin interstellar hydrogen to feed a fusion engine. These were daring ideas, still far from buildable machines, but they were grounded in known laws. Popular science fiction moved in step. Isaac Asimov, Arthur C. Clarke, Poul Anderson, and others used careful science inside their stories. Clarke also wrote technical essays. In 1945, he described communication satellites parked over one point on Earth's equator, a concept later used worldwide. Fiction and research fed each other. Writers explored social and technical consequences. Scientists borrowed clean images and tested them against math. Detailed studies in the 1,960 seconds pushed the boundary again. Project Orion examined nuclear pulse propulsion in depth, estimating speeds that could cut star trips to decades or centuries instead of millennia. At the same time, work on relativity and energy budgets made limits plain. Close to light speed, time dilates for travelers, and energy needs soar. New proposals beamed light sails, antimatter engines entered the discussion as ways to get high thrust or steady push without hauling impossible fuel loads. Researchers and writers also faced the human side. If a journey lasts longer than a lifetime, who goes? Multi-generational ships would need closed ecosystems, robust repair culture, and fair rules. Psychology, education, medicine, and governance became part of the design. The question was no longer only how to push a hull, it was how to carry a community through deep time. Robotic missions in the 1,970 seconds and 1,980 seconds added practice. Voyager 1 and 2 launched in 1977, visited the giant planets, and then kept flying outward. Decades later, they crossed the boundary where the solar wind gives way to the interstellar medium. They showed how to run instruments for years, manage power as it dwindles, and navigate with long delays. These flights did not reach another star, but they turned interstellar from a word in a book into a measured environment. The conversation kept evolving. Laser propulsion, thin solar sails, and various fusion schemes reappeared across papers and conferences. Freeman Dyson discussed very large habitats and long-term energy capture as ways to support life far from Earth. Carl Sagan explained to wide audiences why a spacefaring future rests on careful science today. The theme stayed steady. Imagine, reduce to numbers, test, repeat. In the 21st century, new projects tried to compress timelines. Breakthrough Starshot, announced in 2015, proposed gram-scale probes with reflective sails, pushed by powerful lasers from Earth. The goal: fly at a significant fraction of light speed and pass Alpha Centauri within decades. The craft would be tiny, the instruments minimal, and the challenge huge beam control, sail materials, pointing, and communications over light years. Yet the proposal showed how older ideas can reappear with updated tools and become concrete engineering tasks. Across this century-long arc, the pattern is clear. Myths sparked interest, fiction framed questions, theory set limits. Experiments and missions taught what actually works in the hard environment of space. Interstellar travel remains beyond our current reach for people, but it is no longer outside science. It has become a field with real equations, test plans, and measured unknowns. Each advance opens a narrow door. Better materials make lighter sails. Improved detectors read fainter signals from nearby stars and their planets. Power systems run longer and safer. Navigation grows more precise. Slowly, the set of not yet items shrinks or shifts. The distances do not change, but our ability to think and act at those scales improves. What began as stories about cannon shots and crystal ships now lives in lab notes, mission designs, and careful timelines. To cross light years, we will still need new propulsion, closed-loop life support, strong shielding, and ways to keep people healthy in body and mind over long spans. We will need machines that fix themselves, plans that survive leadership changes, and knowledge that moves cleanly from one generation to the next. The history of the idea shows that this kind of slow build is how big things happen. Imagination makes the first map, science walks the first meter, and marks the ground so the next steps can follow. Early ideas about starflight grew from stories into a field where physics, engineering, and imagination meet. Each generation inherits the last one's tools and questions, then pushes a little farther. 19th century fiction planted seeds. 20th century thinkers gave those seeds math and hardware. 21st century studies test materials, power, and control. Even bold notions like warp drives or antimatter engines trace their roots to this mix of careful reasoning and creative thought. The thread is steady. Turn wonder into numbers and numbers into plans. That plan meets a hard limit first: propulsion. The rockets we fly today are chemical machines. They burn fuel with an oxidizer and throw hot gas out the back. Newton's third law does the rest. This works well for leaving Earth and moving around our solar system. It is powerful, but not very efficient. Engineers describe efficiency with specific impulse, a measure of how much push you get per unit of propellant. Chemical engines have a ceiling there. To reach even a small fraction of light speed, a chemical ship would need absurd amounts of fuel. More fuel makes the ship heavier, which demands more fuel again. The loop feeds on itself until the idea breaks. Fast hardware shows the gap. The Parker Solar Probe, our quickest craft relative to the Sun, has reached speeds of hundreds of thousands of miles per hour. On Earth, that is astonishing. Against the speed of light, it is tiny. At such a pace, a trip to Proxima Centauri would take thousands of years. Numbers like that turn Go to a Star from a mission plan into a story that outlives many nations. So engineers look beyond chemistry. One path is nuclear. A nuclear thermal rocket uses a reactor to heat a light propellant like hydrogen, then expands that hot gas through a nozzle. The exhaust leaves faster than in chemical engines, so the ship gets more push for the same propellant mass. Another path is nuclear pulse propulsion, studied as Project Orion. Tiny nuclear charges fire behind a strong plate, each pulse adding speed. Both ideas are far more efficient than chemical flight. Both face serious hurdles, materials that survive heat and radiation, reliable control, and the political and legal limits on nuclear devices in space. Ion propulsion sits on another branch. It uses electricity to speed up charged atoms and shoots them out at very high velocity. Thrust is gentle, but it builds over months and years. Missions like Dawn showed how this works around asteroids. Ion engines are excellent for deep work inside the solar system, where patience wins. For stars, the thrust is too low to reach useful fractions of light speed without big new advances in power and mass. Energy is the deeper wall. Pushing even a small craft to 1/10 light speed takes an amount of energy that rivals human use over long spans. You must store that energy safely or supply it from afar. Then you must slow down at the end, which takes more energy again. On the way, the ship meets dust and cosmic rays. At high speed, a grain smaller than sand can hit with the punch of a bullet. Shields add mass. Mass lowers speed. Every fix has a cost. Antimatter looks like a way around that. When matter meets antimatter, almost all of their mass becomes energy. In principle, that is the most compact fuel you can have. In practice, we can make only tiny amounts in labs at huge cost. Storage is also hard. Antimatter cannot touch normal matter, so it must be held in perfect electromagnetic traps. A leak would destroy the fuel and, likely, the vehicle. As a concept, it is powerful. As a working system, it remains out of reach. Sails offer a different idea. Carry no propellant at all. A thin, reflective sheet can catch sunlight or a beam from a powerful laser and ride that pressure, gaining speed, slowly but steadily. Small tests in our system have already flown sails. The beamed version takes that further, aiming ground or space-based lasers at a very light craft. If the sail can survive the heat and stay aligned, speeds of a few percent of light might be possible for gram-scale probes. But building and steering the laser array, keeping a large beam tight across light years, and talking to a tiny, fast target are all major challenges. Crewed flight adds weight everywhere. People need air, water, food, waste loops, shielding, medical care, and room to live well enough to stay healthy. Every kilogram added to protect life must be pushed and later slowed. Robots are lighter and tougher. They do not mind silence, cramped quarters, or years in the dark. That is why first steps beyond the sun's reach will almost certainly be robotic, even as we design habitats and systems with people in mind for later. For now, our rockets, chemical, nuclear, thermal, and test beds, electric, are tuned for the solar system. They measure distance in millions or billions of kilometers, not light years. With current and near-term technology, human starflight is not practical. Robotic probes might cross the gap on timescales longer than a civilization's memory. Closing that gap for people will require propulsion that is faster and thriftier, power that lasts, and protection that works without adding crippling mass. Still, the work is fertile. Concepts keep arriving. Giant laser arrays to push swarms of tiny sails, fleets of smart probes that share data and act together, fusion engines with steady, long burn, speculative space-time tricks like warp metrics that shift distances rather than speeds. Most of this is beyond what we can build. Some is beyond what we can yet prove in physics. Yet thinking through these ideas sets targets for materials, optics, power electronics, and control. Naming limits is not a failure of imagination. It is how we choose the right problems. The laws of motion, energy, and light speed do not bend for wishful thinking, but they allow many routes if we respect them. Step by step, we learn to run machines for decades, to close life support loops tighter, to harden systems against radiation, and to navigate with tiny, precise course changes over huge distances. Each improvement turns too far into not yet. In this light, rockets to the moon and probes to the giants are not small wins. They are rehearsals. They teach how to live with delay, to trust autonomous systems, and to design for failure and recovery far from help. They show how careful timing beats brute force, and how small corrections early save fuel and risk later. They build the culture needed for projects that last longer than trends. The path forward is plain, even if the timeline is not. Either we invent new propulsion that changes the speed and energy math, or we accept journeys that span generations and design ships and societies to match. Both routes demand steady work, clear thinking, and patience. Space does not soften for us. We must grow to fit it. The thought of using nuclear power to push a spacecraft took hold as soon as we learned how much energy sits inside the atom. From that point, engineers and physicists began sketching ships that looked nothing like chemical rockets. Instead of burning fuel, these craft would tap nuclear reactions, which pack millions of times more energy per unit mass. The promise was steady, higher speed travel across the deep, where ordinary engines fade. Among the boldest plans was Project Orion in the late 1,950 seconds and early 1,960 seconds. The idea was to fly by firing a series of small nuclear charges behind a craft and catching each blast on a thick pusher plate. Shock absorbers would turn jolts into smooth acceleration. In theory, this pulse drive could lift huge payloads and keep adding speed for a long time, far beyond what chemistry could do. Early studies even sketched paths that might reach nearby stars in spans a person could count in decades, not millennia. Reality pushed back. Detonations in space raised safety and fallout concerns, and the 1,000 963 partial test ban treaty ended any chance of full-scale trials. Engineering was fierce. Plates must survive hundreds or thousands of blasts. Timing must be exact, structures cannot crack under repeated stress, and crews must be protected from radiation. Even so, Orion left a deep mark by showing how nuclear energy could change mission, scale, and speed if the rest of the puzzle could be solved. Work then moved toward engines, not explosions. Nuclear thermal propulsion uses a compact reactor to heat a light propellant, often hydrogen, and expel it through a nozzle. The push is steady and far more efficient than chemical flight. Mid-century tests under the NERVA program showed such reactors could run and deliver high performance for long periods. That makes them strong candidates for fast cargo, crewed trips to Mars, and heavy missions to the outer planets, even if their speeds are modest for interstellar goals. Another branch is nuclear electric propulsion. Here, a reactor makes electricity for ion or other electric thrusters. The thrust is gentle but very efficient, so a spacecraft can fire for months or years and build speed slowly without huge tanks. This approach suits deep robotic work, long surveys of distant moons, asteroid missions, and probes edging toward the solar boundary with power to spare for instruments and communications. With reliable space reactors, light radiators to dump heat, and durable thrusters, nuclear electric systems could become the backbone for mapping the path toward interstellar space even if they do not cross it quickly. Over time, ideas at the edge appeared. Antimatter-catalyzed microexplosions would use tiny bits of antimatter to trigger efficient nuclear burn in normal fuel. Fusion concepts try to ignite light atoms and release deep energy without the mass of heavy fission cores. On paper, these could push a ship to meaningful fractions of light speed. In practice, they ask for leaps we do not yet have, producing and bottling antimatter in useful amounts, building compact, stable fusion systems, and keeping structures intact for decades. Nuclear propulsion carries a weight that is not only technical. The picture of a ship riding atomic fire is both inspiring and uneasy, a reminder that the same force that lights cities can also harm them. That tension shaped the Cold War era when Orion and related studies grew. Military agencies, space planners, and scientists worked side by side while treaties, public trust, and fear of weaponizing orbit set tight boundaries. Any nuclear ship must answer not only engine physics, but also reactor safety in launch and flight, waste heat in vacuum, end-of-life disposal, and clear separation from weapons. Even with these knots, the thread held. Nuclear thermal and nuclear electric designs remain active areas of study, now supported by better materials and improved reactor concepts. Engineers test high-temperature fuels and claddings that survive harsh cycles, build lighter radiators to shed heat, and run electric thrusters for tens of thousands of hours. Each gain moves practical missions, closer cargo to Mars, rapid routes to the outer planets, fast trips to distant dwarf worlds, and maps what still blocks true starflight. Far higher exit speeds without impossible fuel loads, and shielding that stops cosmic rays and dust at velocities where a grain smaller than sand hits like a bullet. Culture keeps pace with the lab. Writers and artists imagine reactors humming in the dark, pusher plates glowing, and sail-like radiators unfolding like wings. Those images feed back into design meetings and research roadmaps, keeping human reasons reach farther, learn more, survive longer close to the math. They also keep the trade-offs honest. Devices in or near space infrastructure, duties to protect future science sites, and the line between civil and military use. Orion stands as both warning and guidepost, hope running hot and rules pulling it back. No human has yet flown beyond low Earth orbit on a nuclear engine, and no interstellar craft has fired a reactor for speed. Still, the groundwork from the mid-20th century frames how we talk about next steps. For trips measured in months inside the solar system, nuclear thermal looks strong. For probes that sip propellant and work for decades, nuclear electric fits. For starflight in human time, we likely need fusion, pulse systems, or beamed power paired with nuclear stages within strict safety and treaty limits. Beneath all of it is a simple energy story. Chemical fuels are easy to handle but weak by mass. Nuclear fuels are hard to handle but rich. Mastering that richness without harm is the narrow road. The path forward is steady. Use near-term nuclear systems to widen our reach in the solar system. Prove long-life power and heat control in flight. Keep testing materials that can take high temperature and radiation, and keep measuring what it will take physically, politically, and ethically to scale from fast missions between planets to the first probes aimed at the stars. Across decades, nuclear propulsion has traced the slow rise of human capability. In the 1,950 seconds, materials were weaker, electronics were simple, and reactor design was young. Bold papers sketched ships that the factories of the day could not build. Step by step that changed. Computer models now test engines before a single bolt is cut. New alloys keep their strength at high heat. Guidance and control are precise and steady. Ideas that once looked like fiction have moved into serious studies, still wrapped in questions of safety, cost, and care for the environment, but closer to real use than ever before. Each small gained better fuels, stronger cladding, lighter radiators, smarter control moves. The line between not yet and nearly possible. The family of nuclear engines shows how many ways atomic energy can become motion. Pulse systems like Orion swap a chain of sharp kicks for raw speed. Nuclear thermal engines heat a light propellant, usually hydrogen, and send it through a nozzle for a smooth push that beats chemical rockets in efficiency. Nuclear electric systems turn reactor heat into electricity and feed ion or other electric thrusters. The thrust is gentle, but it runs for months or years, adding speed the way a slow river carves stone. Each path carries its own trade-offs in speed, payload, complexity, and risk. Mission goals set the choice: fast crewed trips to Mars, heavy cargo to distant orbits, or patient probes that work in the dark where sunlight is thin. Commercial space adds new tools, lighter structures, rapid testing, and lower launch costs, yet the core Starflight problem does not budge. Distances are vast, and useful cruise speeds take real energy. Nuclear methods remain among the few credible ways to raise speed without hauling impossible tanks of propellant. Looking back at past projects helps sort what can be done now from what still needs a leap. The record is a guide. Celebrate what worked, learn from what failed, and keep the parts that can scale safely. Practical effects begin well inside the solar system. A nuclear thermal stage could trim a Mars trip by about half compared with chemical alone. Less time in transit means lower radiation dose and a smaller burden on life support. Crews arrive with more reserves and more margin. Nuclear electric systems open routes that are hard today. Long tours of the outer planets, powered landers on distant moons, slow spirals to high inclination targets, and deep space observatories that need steady power far from the sunday. Extra power on board means stronger radios, richer instruments, and room for autonomy when signals take hours to cross the void. Nuclear electric flight has a calm logic. A compact reactor makes electricity. Converters and radiators manage heat. Thrusters accelerate ions to very high exhaust speeds. The push is small at any one moment, but the engine can run almost without pause, sipping propellant and building speed. The hardware must be tough. Fuels that keep shape, bearings that do not seize, grids that do not erode too fast, and radiators that throw heat to space without folding under stress. Done well, the reward is reach missions measured not by how much propellant you can lift, but by how long you can operate. Pulse concepts still hold a strong pull because their energy density is hard to ignore. The Orion idea, catching controlled nuclear pulses on a thick plate, showed how far energy per mass could be pushed. It also showed the boundaries clearly. Safety is not a footnote. Detonations in space, launch accidents on Earth, fallout, and debris all raise hard questions. Treaties set strict lines. Materials must survive repeated shocks. Timing must be exact. Crews must be shielded without making the ship too heavy to move. The idea marks a point on the map. High speed is on the table, but only if ethics, law, and engineering walk together. Culture and lab work have always talked to each other here. Mid-century writers pictured fleets of atomic ships and cities between the stars. Those pages taught readers to think in clean units: mass, thrust, power, and to ask how a community might live for years in a closed world of metal and light. In return, engineers borrowed those images and tested them with math and hardware. The loop continues. As materials and reactors improve, concepts once tagged as sci-fi show up in careful workshops with real numbers attached. Duty sits beside ambition. A reactor in space must be safe at launch, safe in flight, and safe at the end. Waste heat must be dumped without cooking the craft. Radiators must be big enough, yet light. Radiation must be held inside shields, so crews and electronics survive. Orbits must avoid creating long-lived debris. Ground rules and public trust matter. They shape design choices as much as metal and wire. Good rules do not stop exploration. They keep hard problems honest and prevent harm that would close doors for years. Nuclear ships reshape how we think about living far from Earth. A large, steady power vehicle would carry closed loops for air and water, small gardens for food and morale, tools and parts for repairs, and training that passes skills from one crew to the next. Autonomy grows because light speed delay turns help lines into slow mail. Crews learn to diagnose, patch, and decide with limited outside input. Even robotic craft need the same habits coded into their systems. Detect faults early, reconfigure, and keep working. Research fills in the details that make or break these plans. High-temperature fuels are tested under cycling loads. New claddings resist swelling and cracking. Power converters trade mass for reliability. Radiators try new shapes to throw more heat with less area. Electric thrusters run for tens of thousands of hours on stands to prove they can last. Digital twins, faithful software copies of the hardware, let engineers trial failures and fixes before a mission ever flies. Each result updates the design loop and trims risk. Lessons from earlier decades still steer the work. Chemical rockets are simple and proven, but weak by mass. Nuclear systems are rich in energy, but hard to handle and harder to win public trust for. Fusion, antimatter, and beamed power sails hint at higher speeds, yet they ask for breakthroughs in storage, control, and materials. The path, then, is staged. Use near-term nuclear thermal to speed human missions in the inner system. Field nuclear electric for deep robotic work and outer planet tours. Keep pushing on advanced ideas in the lab, tied to measurable goals rather than wish lists. The appeal of nuclear starships comes from scale. A pulse-driven craft could be the size of a moving town. A nuclear electric vehicle might unfold wide, dark radiators that glow faintly as they work. These images stretch the mind in a useful way. They force planners to count food, water, spare parts, and stories, the human pieces that keep crews whole on long arcs through quiet space. They also force careful thinking about how a ship ends its life without leaving a hazard behind. Each concept Orion pulses, thermal engines, electric thrusters, adds to a shared base of knowledge. We learn what lasts, what fails, and why. We learn where the trade-offs sit. More shielding adds mass. More mass lowers speed. Lower speed lengthens time and radiation. Clear numbers make choices plain. They turn broad hopes into designs that can be built, tested, and improved. Taken together, nuclear propulsion is both tool and mirror. It shows how far careful work can carry an idea that began as a sketch. It shows how story, policy, and lab results pull on each other. It shows that chemical fuel will not take us everywhere we want to go, and that nuclear energy, while richer and harder to manage, might. Most of all, it keeps a steady long view. First faster trips to Mars and the outer planets, then durable probes edging past the sun's reach, and later, if the parts come together, machines and perhaps people built to hold a quiet, reliable course between the stars. Fusion starships begin with a clear idea. Use the same kind of power that runs the sun to push a ship fast enough to cross the darkness between stars. Chemical rockets hold too little energy in their fuel. They are strong for launches and good for trips inside our solar system, but they slow down badly when distance grows. Fusion promises far more energy in far less mass. If we can control it, a ship could accelerate gently for years, coast, then turn and slow down at another sun, finishing a journey that fits within a working life rather than many lifetimes. Fusion joins light atoms into heavier ones and releases energy. Stars do this because their cores are extremely hot and dense. On Earth, we try two main routes. Magnetic machines trap a thin, very hot gas plasma inside strong magnetic fields so its particles can collide and fuse. Inertial machines focus short, powerful bursts from lasers or particle beams onto tiny fuel pellets, squeezing and heating them for a brief moment of fusion. Both methods have made small flashes. The hard part is steady control and net gain, getting more useful energy out than it takes to run the system. The physics allows it. The engineering is demanding. Engineers began to sketch fusion ships as soon as fusion power was discussed. In the 1,970 seconds, a study called Project Daedalus asked what an unmanned fusion probe could do if the core ideas worked. The plan used rapid micro-explosions from pellets made of deuterium mixed with helium-3. Magnetic fields would catch the blast and throw it backward as exhaust. The craft would be hundreds of meters long and carry thousands of tons of fuel, yet in return it might cruise at a meaningful fraction of light speed and reach a nearby star in about half a century. A later U.S. concept, Project Longshot, aimed at Alpha Centauri and added a small fission reactor for ship power, while the main push still came from fusion pulses. Taken together, these studies turned dreams into numbers and showed what a real interstellar engine might demand. Helium-3 appears often in these plans. When deuterium fuses with helium-3, the reaction makes mostly charged particles rather than neutrons. Charged particles can be guided by magnetic fields and shaped into a fast exhaust without first dumping most of the energy as heat. Fewer neutrons also mean less damage to the engine and less activation of the ship's structure. The trade-off is fuel supply. Deuterium can be distilled from water. Tritium is rare and must be bred. Helium-3 is scarce on Earth. People often point to the moon's soil and the giant planet's atmospheres as possible sources, though collecting it at scale would be a major program on its own. Other designs swap rapid pellets for a steady direct fusion drive. Here, the reactor keeps a hot plasma burning while magnetic fields both confine it and shape the exhaust. Thrust and electric power come from the same core. Operators could tune the engine for more push or more electricity as the mission needs change. The gains are fine control and fewer moving parts than a pellet machine that has to fire many times per second. The costs are the classic fusion problems: stable confinement, materials that endure heat and radiation for years, and a compact system light enough to fly. A fusion ship must also manage simple but harsh facts of space. The engine gives off a lot of energy. Some becomes thrust. Much turns into heat inside the craft that must be sent away. In space, there is no air or water to carry heat off. Radiators must throw it out as infrared light. That means large, light panels or loops that run hot without failing. The ship must shield its electronics, instruments, and if it has them, its crew from radiation. At high speed, even a dust grain can hit like a tiny bullet. Designers add layered bumpers at the nose, consider magnetic fields to deflect charged particles, and choose paths that avoid dense dust lanes. Every safety layer adds mass, and mass pushes against speed, so the balance must be honest and tested. The rewards are clear. With fusion, nearby stars become reachable in decades rather than ages. A probe could sample the thin gas between stars, image another system up close, and send data home while the original team is still alive to study it. For people, the timeline stays long but becomes human. A ship could accelerate for a few years, coast, and then decelerate to meet a target sun, using closed-loop life support and rotation for artificial gravity. The problem shifts from impossible time to long time, which is still hard but can be planned. Fusion research on Earth maps the road. Stronger, lighter, superconducting magnets allow tighter, more efficient magnetic fields. Better lasers and optics improve the timing and symmetry of pellet shots. New claddings, ceramics, and composites withstand higher temperatures and resist radiation damage. Digital tools let engineers build twins of engines in software, push them until they break, then change the design before any metal is cut. None of this makes a starship by itself. Together, they shrink the unknowns. Turning fusion energy into push can follow different paths. In an inertial fusion rocket, pellets arrive at a fast pace, are ignited by lasers or particle beams, and make tiny, regular bursts whose hot ions are caught by magnetic fields and sent backward. In a magnetic engine, the plasma is kept hot and confined, while a magnetic nozzle directs the fastest particles as exhaust. Either way, the exhaust leaves at very high speed, which means the ship needs much less propellant mass to gain the same delta V. That is the heart of fusion's promise. High exhaust velocity cuts the fuel spiral, where more propellant makes a ship heavier, and the added mass forces still more propellant. Navigation and control are as important as raw power. A ship must aim for where a star will be decades from now, not where it is today. It must hold course with tiny corrections, track time with great accuracy, and stay healthy without help. Communication cannot be live. Signals take years across light years. Autonomy is not a feature, it is a requirement. Onboard systems will watch the reactor, tune the fields, fold and rotate radiators, reshape shields, run science programs, and report status while the ground team waits for replies. Good autonomy still needs clear rules and backups so small faults do not grow into mission failures. Fusion engines can also run the ship. Electricity drawn from the core can power environmental controls, cryocoolers for sensitive detectors, centrifuges for spin gravity, high-gain transmitters, and the tools that keep a long mission going. Spare heat can keep lines from freezing in deep cold. Power margin, the difference between what you can make and what you need, adds safety and enables better instruments. Stopping at the other end takes planning. The simplest method is to turn the ship and thrust in the other direction. Magnetic sails offer another tool. A loop of wire can project a magnetic field that drags against the thin, ionized gas between stars and bleeds off speed without using fuel. Close to the destination, a magnetic or electric sail can also push against the new star's wind for final approach. These methods do not replace a drive. They reduce the fuel needed for braking and add options if the engine must throttle down. Human missions add biology to physics. Radiation dose must stay low over many years. Habitats must recycle water and air to very high levels. Food production can be partly on board to reduce resupply needs and provide fresh nutrients. Social design matters. Routines, privacy, training, and shared work keep minds steady in a small world. A ship that runs for decades must be a place to live well, not only survive. Fuel flows tie propulsion to exploration policy. Deuterium is easy to get from water. Tritium can be bred inside reactors, often using lithium blankets. Helium-3 is scarce on Earth, so attention turns outward. Lunar soil may hold small amounts implanted by the solar wind. Giant planets' air may hold more. Any real supply chain would require major missions to mine, process, and ship fuel, which in turn would build a broader space economy before true starflight begins. Hazards scale with speed. At 1/5 the speed of light, even tiny dust hits release high energy. Layered shields, thin front foils to vaporize small grains, gaps to let the vapor spread, and stronger bumpers behind help. Magnetic fields can bend charged particles away from living spaces and key circuits. The ship's skin can act as a sensor, listening for impacts and guiding repairs. A design must assume that some hits will happen and include ways to patch and reroute. All along, the Earth's side benefits. A push to control fusion for space would speed progress in fusion power for cities, which could shift the world's energy balance and cut carbon. Work on high-temperature materials, heat rejection, and compact power systems would help industry, transport, and science on the ground. Advances in autonomy, fault detection, and long-life electronics would spill into many fields. Design choices reveal honest trade-offs. Deuterium-tritium burns more easily, but makes many neutrons that damage structures. Deuterium-helium-3 runs cleaner, but is harder to ignite and harder to source. Inertial engines promise precise pulses but need complex pellet factories and high-power drivers. Magnetic engines promise smooth control but depend on stable plasmas and strong, light coils. A Daedalus-style probe might spend its fuel on speed and fly through a target system without stopping. A Longshot-style probe might reserve fuel to brake and accept a longer cruise. No single answer solves every mission. Even with a strong engine, interstellar travel is a venture in patience. At 20% of light speed, a ship takes more than 20 years to reach the nearest star, plus the time to slow down. That timeline demands robust parts, careful margins, and a culture that can pass knowledge across teams. It also changes what mission success means. The work is not only a launch, it is decades of care for a machine far beyond help. The likely path is step by step. First come long-life power packages tested in Earth orbit and deep space to prove heat rejection and control. Then nuclear electric craft that travel far from sunlight and run for years with gentle but steady thrust. Beamed energy tests refine the pointing and control needed for light sails. As parts mature, a small fusion-powered stage flies in the outer solar system, where help is far away but not impossible. Only after many such steps would a true interstellar probe leave, carrying a proven core, redundant systems, and a plan to aim, adjust, and brake at its goal. Fusion does not make the stars close. It makes them closer than they are today. Between a single human life and the sweep of the galaxy lies a space where engineering can matter. The fuels exist. The laws of physics allow the trip. What remains is control of plasma, strength of materials, smart heat management, reliable autonomy, and the will to run projects that last longer than fashion. Piece by piece, those parts can be built. When they fit, a ship can leave the sun's wind behind and keep going, still slow compared with light, but fast enough to turn distant points into places with weather, seasons, and years of their own. Antimatter propulsion begins with a simple, startling idea. Every particle of matter has a twin with the same mass and an opposite charge. Electrons have positrons. Protons have antiprotons. When a particle meets its twin, both vanish and their mass becomes energy. Einstein's rule energy tied to mass by the square of the speed of light means even tiny amounts release enormous power. A gram-scale meeting of matter and antimatter would yield energy on the order of a large nuclear weapon. Chemical fuel cannot come close. Even fission and fusion lag far behind in the share of mass they turn into useful energy. On paper, that efficiency could push a ship to a real fraction of light speed and pull the nearest stars onto a human timeline. The promise is clear. Far less propellant, far more speed, and a smaller, lighter engine for the same work. With sustained thrust, a craft could accelerate for months or years, coast, then flip and decelerate to meet another sun. Trips that would take millennia with chemical rockets might shrink to decades. A probe could pass Alpha Centauri within a working life. A crewed craft would still face a long journey, but the span would fit inside a human lifetime, rather than many. The obstacles are just as clear. We do not have the fuel. Antimatter today is made in particle accelerators in vanishingly small amounts. Facilities can collect nanograms of positrons or antiprotons per year at very high cost, and storing even that much is difficult. A starship would need millions to billions of times more. The energy to make gram quantities would be vast. The money and infrastructure would be unlike any project built so far. Even a small interstellar mission would demand kilograms of antimatter, which is far beyond current production by time, cost, and power. Storage is the next wall. Antimatter cannot touch ordinary matter. The instant it does, it annihilates. There is no safe tank with a wall to lean on. The only containers that work are electromagnetic traps that suspend charged antiparticles inside a near-perfect vacuum. These penning-like traps use electric and magnetic fields to hold the fuel away from anything it could touch. They work for picograms to nanograms in quiet labs. Scaling them to grams or kilograms that a ship could carry is a problem we do not know how to solve yet. Fields must stay stable for years. Vibrations, a dust mote, a single glitch could release energy at levels no structure can survive. Redundancy, fault detection, and fail-safe dumps would be essential, and the mass and complexity of those systems would eat into any performance gains. Turning raw annihilation into directed thrust is another hard step. When antiprotons strike protons, the energy comes out mostly as high-energy particles and gamma rays. The charged particles can, in principle, be bent and shaped by magnetic fields into an exhaust. The gamma rays are harder. They carry a large share of the energy, can damage electronics and cells, and are difficult to reflect or focus. Several schemes have been proposed. One is to let the annihilation heat, a separate working fluid, often hydrogen, into a hot plasma and throw that out through a nozzle. Another uses a magnetic nozzle to guide the charged fragments of the reaction directly, trying to capture the momentum without first dumping all the energy as heat. Both paths are still theory heavy. None has been proven at the scale or efficiency a mission would need. Because of these control problems, some designs trade pure antimatter drives for antimatter catalyzed systems. Here, tiny doses of antimatter micrograms or less would trigger fission or fusion in ordinary fuel. The antimatter serves as a match, not the main fire. That approach could cut the amount to be produced and stored by many orders of magnitude, while still giving higher exhaust speeds than chemical rockets. It adds moving parts and fresh risks, but it softens the sharpest edges of storage and gamma control. Speed brings its own hazards. At 1/10 of light speed, even a grain of dust hits like a bullet. At higher fractions, the damage rises quickly. A ship must carry layered shields, a thin sacrificial bumper to vaporize small grains, a gap to let the vapor expand, and a stronger layer behind to catch the plume. Magnetic fields can help steer charged particles away from vulnerable areas. The ship's skin can act as a sensor, listening for impacts and routing repairs. These protections add mass, and mass slows you down. Navigation must be precise. Communication will be slow. At interstellar distances, messages take years, so autonomy is not a feature, it is a requirement. Guidance, health checks, reactor control, thermal management, and science tasks must run themselves while Earth waits for replies. Relativity enters quietly but firmly. As speed increases, time on board runs a little slower than time on Earth. For the crew, the trip might feel shorter than it measures to mission control. That helps humans cope with decades in flight, but it breaks real-time planning. It also shifts how we frame mission goals. You cannot steer by conversation at light-minute or light-year delays. You must program judgment into the ship. Economics and power supply loom over all of this. Making antimatter is not just slow, it is wasteful. Only a small fraction of the input energy becomes trapped antiparticles, and catching them safely is hard. Producing grams would likely take power on the scale of nations and money on the scale of global programs. Building factories, traps, launch systems, and safe handling paths would demand international cooperation, clear rules, and public trust. The dual-use nature of antimatter complicates that picture. Energy dense enough for starflight is also energy dense enough for weapons. Controls, treaties, and watchful verification would have to grow alongside any technical progress. Radiation is a constant concern. Antimatter reactions bathe a vehicle in gamma rays and other energetic particles. Electronics need shielding and careful layout to prevent latch-ups and failures. If people fly, their health depends on dose staying low. Shielding works, but it is heavy. Designers must trade thickness and mass against speed and mission time, and may combine passive material shielding with active magnetic deflection to save weight. The upside of this research path is not only future speed. Work on antimatter already helps medicine and physics today. Positron emission tomography uses positrons to image tissue and diagnose disease. Particle traps, ultra-high vacuum, strong magnets, and precision timing improve labs across many fields. Energy conversion techniques developed to tame extreme radiation can make power systems and electronics more robust on Earth. Even if Starflight waits, these tools feed back into daily life. Mission architecture would change with a true antimatter stage, because the fuel mass shrinks for a given delta V. More of the vehicle can be payload, instruments, shielding, habitats, and supplies. A craft could break at a new star rather than flash through. It could carry landers or small probes and drop them along the way. It could afford a thicker nose shield and still meet speed targets. Ideas for braking, such as magnetic sails and electric sails, become more attractive too. A big loop of wire can throw a magnetic field outward and drag against the thin, ionized gas between stars, shaving speed without spending propellant. Near a destination, similar fields can push on a star's wind to help with final approach. These aids reduce the antimatter the mission must reserve for the endgame. Designs split by fuel choice. Antiproton engines couple strongly to ordinary matter, deliver a dense burst of energy, and tend to produce both charged particles and gamma rays. Positron concepts are easier to make in small amounts and simpler to store, but the output skews even more to hard radiation that is difficult to turn into thrust. Hybrid ideas layer antimatter triggers on top of fission or fusion to find middle ground. Each path has trade-offs in control, safety, storage, and efficiency. No single scheme dominates on paper, and none is ready in practice. Safety sets the tone for everything. Even a tiny leak is not minor when your fuel annihilates on contact. Containment must be multiply redundant. Traps need independent power and fast automatic safing sequences. The system must sense drift, dump fuel to a safe location, and hard isolate remaining stores within fractions of a second. Ground operations must keep people and equipment out of harm's way. Launch and ascent add risk. Vibration, heating, and shock can disturb fields. Many studies therefore put antimatter handling in orbit or beyond, fed by dedicated cargo runs to keep launch risks low. Policy follows close behind. Any real antimatter program would raise questions about who builds it, who audits it, how waste and accidents are handled, and how the knowledge is shared. Public trust would hinge on transparency and a track record of safe, small steps. The experience of nuclear power and spaceflight suggests a path. Start with uncrewed tests, build layers of independent review, publish findings widely, and design failure into the model so that when things go wrong, they fail safe, not catastrophically. For all its distance from hardware today, antimatter work maps a useful long road. Near-term research focuses on better traps, colder vacuums, stronger magnets, and gentler ways to handle tiny amounts. Midterm work explores catalysis, how small doses can ignite fusion or fission more cleanly and efficiently than lasers or neutron sources can. Far-term studies shape engine nozzles, radiation shields, and heat rejection for hypothetical vehicles. then prune concepts that cannot survive honest numbers. Along the way, progress in high-power electronics, fault-tolerant control, and autonomous decision-making makes every space mission sturdier. Antimatter propulsion forces us to be clear about what we can build and what we can only sketch. It asks for energy and money on scales we have not yet committed to science outside of wartime or global projects. It also offers a measure for ambition. If we want the stars as places rather than points, we must either invent engines like this or accept journeys that last longer than one life and design ships and societies to match. In practice, the likely sequence is layered. First, better electric and nuclear thermal stages for faster work inside the solar system. Then beamed sails and fusion-based drives for robotic probes that press into interstellar space. Then, much later, antimatter and catalytic rolls that shrink engines and raise exhaust speeds. And only after many steps, a true antimatter main drive. The idea remains compelling because it speaks to scale. Converting nearly all of a fuel's mass into thrust is the cleanest possible answer to the distance problem. The costs and risks are just as large. Production is slow and expensive. Storage is delicate. Control is complex. Radiation is harsh. Speeds bring new dangers. Laws and ethics must be written and followed. Yet the science does not forbid it. The steps are hard, but not magical. Each can be studied, tested, and improved. Antimatter propulsion is both tool and symbol. It is a tool because, if mastered, it could carry instruments and someday people to nearby suns on timelines we can plan for. It is a symbol because it shows the outer edge of what engineering might do with known physics. It challenges us to build carefully, to weigh risk against reward, and to keep our aims steady for longer than a news cycle. If we learn how to make, hold, and guide this most concentrated fuel, we will have taken a quiet, decisive step toward turning star maps into travel plans, still slow compared with light, but fast enough to cross the dark in a single lifetime, and to bring back the first close looks at other worlds that shine, for now, only as distant points. Light can push a ship. A photon has no mass, yet it carries momentum, and when streams of photons strike a shiny surface, they press on it very gently. In the vacuum of space, where there is almost no drag, that gentle press can add up. A solar sail spreads a thin, mirror-like sheet and lets sunlight give it a steady nudge. A laser sail does the same, but catches a focused beam from a powerful array. Neither carries propellant. Both turn light into motion. The push is tiny each second, but it never needs to stop, so speed grows day after day. Where a chemical rocket gives a short, violent shove and then coasts, a sail trades that burst for a quiet, constant climb. Solar sailing is simple in spirit and tricky in practice. The sail must be extremely light, very reflective, and wide, sometimes hundreds of meters across, yet strong enough to hold its shape. It must unfold cleanly after launch, without tears or creases, and keep its surface smooth as it warms in sunlight and cools in shadow. Once open, it steers by tilting. Change the angle a few degrees, and the direction of the photon push shifts, much like a boat tacking into the wind. Over weeks, this lets a craft spiral inward toward the sun, drift outward to the outer planets, or slide sideways to meet a comet or asteroid. The idea has deep roots. Early thinkers in the late 19th and early 20th centuries guessed that light pressure could move objects in space. Small tests in Earth orbit later proved sunlight can change a satellite's path. In 2010, Japan's Icarus mission unfurled a sail and flew by the inner planets using sunlight alone, and its thin film cells drew power right from the sail. The Planetary Society's light sail flights deployed bright, square sails and showed how careful pointing, rotating the craft during each orbit lets sunlight raise or lower altitude without a drop of fuel. These were modest craft, but they turned a sketch into working hardware and taught lessons about packing, unfolding, and control. Laser sailing extends the same physics. Instead of waiting for the sun, a ground or orbital array would fire a tight beam at a small, strong, highly reflective sail. The beam delivers far more pressure than sunlight, so a gram-scale probe with a meter-scale sail could be pushed to a high fraction of light speed in minutes or hours, then coast for decades. Concepts like Breakthrough, Starshot picture tiny craft racing toward Alpha Centauri, flashing past a planet, snapping images, sampling local plasma and dust, and sending data home on a tight power budget. The basic math is sound. The difficulty is building a beam that stays focused, a sail that survives the heat, and a control system that keeps both aligned while the probe accelerates away. Materials sit at the center of both approaches. A good sail reflects most of the light that hits it, spreads heat so it does not wrinkle or burn, and resists tiny impacts from dust. For laser work, the film must also handle intense power at specific wavelengths. Engineers chase micrometer-thick films with special coatings that reflect well and shed heat, edges that do not curl, and frames that fold small for launch but open flat in space. The structure must be stiff enough to hold shape and yet light enough that a photon's small push makes a real difference. Pointing and control are quiet arts. A sail uses small actuators, moving masses on booms, or patches that can change reflectivity to trim attitude by fractions of a degree. For a laser sail, control becomes sharper still. The beam must stay locked on a target that is tiny, far away, and speeding up fast. Adaptive optics must clean the beam as it climbs through air. Multiple lasers must combine cleanly and adjust in real time based on faint signals from the sail. Any slip risks pushing off-center, warping the film, or missing the target completely. The gains are compelling. A solar sail never runs out of fuel while sunlight shines. That makes it ideal for long surveys, holding station above a pole, visiting several asteroids in sequence, drifting over the sun's poles to watch its wind, or scouting the far reaches beyond Neptune without waiting for rare planetary alignments. A laser sail, if built, could launch swarms of tiny probes toward nearby stars. Many craft mean many chances for success, more sky covered, and a steady trickle of data years later. Without tanks, more mass can go to instruments, shielding, or small landers. The physics is simple to state, but slow to master. A single photon's push is tiny, yet billions upon billions strike a large sail each second. The force is small, the acceleration smaller, but the time is long. What matters most is area, reflectivity, mass, and light intensity. Double the area and you catch more photons. Cut the mass, and each nudge moves you more. For sunlight, distance from the sun sets the ceiling. For lasers, the ceiling comes from beam power and the sail's ability to survive the push without buckling or melting. Practical work has revealed pitfalls. Deployment is delicate. A crease can become a weak line. A snag can twist a corner and spoil control. Teams use careful folding patterns, slow spin to pull the sail flat, and cameras to check shape as it opens. Micrometeoroids poke pinholes. Films must tolerate small damage without tearing. For laser drives, heat is the chief enemy. Even a tiny fraction of absorbed light can warm a thin film quickly. Designers spread heat, reflect strongly at the beam's color, and, when needed, pulse the beam rather than holding it steady. Navigation is steady work, too. A sail bound for another star must launch on a path aimed at where the target will be decades later. Commands from Earth arrive late, so autonomy is not a bonus, it is required. Onboard systems sense attitude, check sail shape, trim angles, and keep the course while ground teams watch long trends. For a laser sail, the first minutes matter most. The array and sail must dance together. After that, the probe coasts in silence and sends back data on scarce power. Because sails avoid propellant, they also change how we plan closer missions. A sail can slowly raise or lower an orbit without burns, station keep upstream of Earth against solar wind, or give CubeSats a low-cost way to climb. Deep space versions could dive near the sun to pick up speed and slingshot outward, or loiter where sunlight is faint while still making progress. A laser array, once built, could double as a power beamer, charging distant probes, nudging small craft, or delivering energy to a base on a shadowed moon. Safety and environment matter. A wide sail reflects strongly and is hard to track if folded or torn. Traffic rules must account for it. End of mission plans should fold and lower a sail to a safe burn-up or park it in a graveyard orbit. A ground laser array must be sighted and managed to keep aircraft, satellites, and eyes safe, with hard limits, shutters, and tracking that turns the beam off if anything crosses the path. Clear rules and open data build trust and keep the field open to more teams. Hybrid plans are likely. A probe might launch on a conventional rocket, deploy a solar sail to climb outward, then catch a laser beam for a final push. Another might use sunlight near the sun for a sharp boost, then fly on a dim beam farther out. Fleets of small, smart probes, each with a thin sail and a few grams of instruments, could spread along different paths and share data as a group. A few would fail. Enough would succeed to map the way for larger craft. None of this removes limits. A sail is nimble, but not quick to stop. It cannot hover freely or reverse without care. A laser array is a massive build with demanding optics and control. But the limits are clear and honest, and they point to shared work, better films and coatings, lighter frames, smarter control, stronger lasers, sharper mirrors, and more robust autonomy. Each improvement helps other corners of spaceflight too, from power beaming to thermal control and precision pointing. In a quiet way, sails widen what seems practical. They show that interstellar flight does not require giant tanks. If the craft is light, the sail is strong, and the push is steady. They show that patient acceleration can beat a short, violent burn when distances grow beyond the scale of planets. Most of all, they show that the same photons that warm our faces at noon can, over time, carry small machines, and one day, larger ones far from home. With bigger sails, better beams, and steadier control, the thin pressure of light can turn star maps into routes and distant points into places with seasons and weather of their own. Among the nearby lights of the Milky Way, a few stars sit close enough to feel like first steps. They are not just dots in the sky anymore. With better telescopes and steadier methods, they have become measurable places with distances, temperatures, and best of all, planets we can begin to study from afar. These neighbors are not equally bright or calm, and most are not sun twins. Yet each offers a different path for learning how other systems work and what kinds of worlds might circle them. Alpha Centauri leads the list. It is a system of 3 stars bound together by gravity. Alpha Centauri A looks much like our sun in size and light. Alpha Centauri b is smaller and cooler, and the pair orbit one another in a long, stable loop. Farther out is Proxima Centauri, a dim red dwarf that happens to be the closest known star to us. Light from Proxima takes a little over 4 years to reach Earth. For photons, that is quick. For rockets built with chemical fuel, it is vast, which is why interstellar missions demand new ways of moving through space. Proxima Centauri matters for another reason. It hosts at least one known planet, Proxima b, that orbits in the star's temperate zone. Because Proxima is faint, the planet hugs close to stay warm. That orbit likely keeps one side in constant day and the other in constant night. Between the two extremes lies a narrow ring, the terminator, where temperatures might be mild enough for liquid water if air and oceans can move heat around. Proxima b may be harsh, but its nearness makes it a priority target for close study with future instruments and, one day, fast robotic probes. A little farther sits Barnard's star, about 6 light-years away. It is an old red dwarf, much dimmer than the sun, famous for sliding across the sky faster than most stars when viewed over decades. Evidence points to a cold super-Earth in a short orbit. Sunlight there would be weak, and the surface, if rocky, would likely be frozen. Even so, cold does not erase all possibility. In our own system, icy moons hide deep oceans under crusts of ice. A nearby super-Earth could teach us how heat from a planet's interior, salts, and pressure can sustain water in sheltered layers far from direct starlight. Other neighbors fill out the map. Wolf 359, roughly 8 light-years away, is a very dim red dwarf that needs a telescope to study. Lalande 21185, at a similar distance, is another small, long-lived star under close watch for planets. Sirius, the brightest star in our night sky, lies a touch farther. Its shine comes from both proximity and power, and it has a compact white dwarf companion, Sirius B, the dense core left behind when a star runs out of fuel. Even where no mild, rocky planets are confirmed, these systems help calibrate our expectations and test our tools. Distances set the core challenge. Fast probes inside our solar system travel at tens of kilometers per second. At that speed, a ship would need tens of thousands of years to cross a few light years. Mars is months away. Alpha Centauri is more than 4 light years. This simple contrast drives work on new propulsion, nuclear, thermal, and nuclear electric engines for quicker inter-system trips, fusion concepts that promise higher exhaust speeds, and light sails pushed by powerful lasers that could accelerate tiny, smart probes to a real fraction of light speed. While propulsion advances step forward carefully, the hunt for nearby planets moves quickly. Proxima b is likely a little more massive than Earth and orbits in days, not months. A day-night lock would create extremes, but winds and currents could smooth a twilight band into a habitable ring. Barnard's candidate planet is heavier than Earth and circles in roughly 8 months. It receives little light and would be bitterly cold at the surface. Yet subsurface seas remain possible if internal heat is strong. These cases widen our view of habitability, moving beyond perfect Earth analogs to a spectrum of niches where water and chemistry might coexist. We find such worlds by watching stars with patience. The radial velocity method measures a star's tiny wobble as planets tug it back and forth. Transit photometry looks for slight, regular dips in starlight when a planet crosses the disk. Used together, these methods reveal mass, size, and orbit. Space telescopes add reach by lifting observations above Earth's blur and holding a steady gaze for long runs. With the right alignment, starlight filtering through a planet's air leaves faint fingerprints, patterns that hint at gases like water vapor or carbon dioxide, and one day, more complex blends. The nature of the host star shapes what is possible on surrounding worlds. Red dwarfs like Proxima and Barnard's are small, cool, and long-lived. Their lifetimes stretch beyond trillions of years. That stability is a gift, but many flare often, bathing nearby planets in bursts of high-energy radiation that can strip atmospheres unless a planet has a strong magnetic field or a thick blanket of air. Sun-like stars are calmer and more familiar, but the nearest good twins are usually farther away. Choosing targets means balancing distance against star type, a nearby red dwarf with active weather, or a slightly more distant, steadier star with a broader, milder temperate zone. Ambitious but focused concepts show how the first interstellar data might arrive. One approach imagines gram-scale probes attached to meter-scale reflective sails. A ground or orbital array of lasers would push each sail for minutes until it reaches a significant fraction of light speed. Then the probe would coast. At those speeds, Alpha Centauri becomes a decades-long trip, not a millennia-long one. A tiny craft cannot carry people, but it can carry cameras, particle detectors, and a radio, flying past planets, tasting the local plasma and dust, and sending home brief bursts of data. Such missions bring quiet, stubborn engineering demands. At high speed, tiny dust grains strike like bullets. Layered shields at the nose and smart routing of sensitive lines reduce risk. Radiation from cosmic rays and flares can degrade sensors and electronics over years. Design must assume parts will age and include graceful fallbacks. Power must last for decades, which favors simple, efficient systems and careful duty cycles. Communication must cross light years, so data rates are modest and delays are long. Guidance cannot rely on quick help from Earth. Onboard autonomy must keep attitude, aim the sail, navigate by stars, and manage health with conservative rules. These nearby systems also carry scientific weight beyond travel. They let us test climate ideas on planets very different from Earth tidally locked worlds, cold super-Earths, and planets baked by flares. They help us learn how air is lost or preserved, how clouds form under strange suns, and how magnetic fields and particle winds shape space weather. If a planet's spectrum shows gases out of balance mixtures hard to explain without ongoing chemistry, then questions sharpen. What processes drive that mix? Can geology do it alone? Could biology be at work? Each step we take to study these stars shapes the tools we build. Better spectrographs resolve slower wobbles and smaller planets. Improved coronagraphs and star shades block more starlight to reveal faint companions directly. Larger arrays on the ground and in space gather more light and correct for atmospheric blur. These advances serve near goals: one more planet measured, one more atmosphere probed, and far goals: a short list of worlds close enough and compelling enough to justify the first probes across interstellar space. Planning for those probes blends caution with reach. A sail mission to Proxima or Alpha Centauri must aim for where a target will be decades from now, not where it is today. It must carry shields sized for the dust in the interstellar medium and a communication system that can beam home faint signals to a patient global network. It needs redundancy and clear safing rules so a fault does not end the journey. The push phase under lasers would demand tight control. The long coast would be marked by quiet housekeeping and periodic check-ins. Near the target, the probe would wake fully, gather images and spectra, and send home its notes across the dark. The cultural meaning grows alongside the engineering. Nearby stars are milestones that test whether we can plan and build for timescales longer than a career and then learn from what we receive. A single close-pass image of a nearby planet's surface, a spectrum that changes with seasons, or a magnetic map of another system's space weather would reshape our sense of place. Even a null result, a dry, airless rock, teaches us how planets diverge and why Earth is rare or common. Studying the composition, age, and motion of nearby stars helps astronomers rebuild the Milky Way's story, how gas and dust formed new suns, how orbits shifted, and how planets spread over time. Red dwarfs such as Proxima Centauri and Barnard's star, which can shine for far longer than the sun, point toward the distant future and the kinds of long-lived systems where worlds may persist for eons. Sun-like stars such as Alpha Centauri A give close comparisons to our own star, showing both familiar patterns and key differences. In this way, observations act as mirrors and windows at once. They reflect our solar system's nature while opening views to very different paths of stellar and planetary evolution. The work is too large for any single team. Ground observatories in Chile, space telescopes such as the James Webb Space Telescope, and bold laser sail proposals only thrive when agencies, universities, companies, and citizen groups share time, data, and expertise. Pooling resources lets us cross-check results, improve instruments, and plan long campaigns. Cooperation turns scattered projects into a common roadmap that reaches beyond the sun's light. Curiosity drives this roadmap, but so does need. People have long looked up and felt the urge to go farther. With better tools, that urge becomes a practical question. Could we leave home for another sun? The answer matters only if there is a place to go. Without a world that can host people for the long term, interstellar travel is a story without a destination. So the search begins with Earth. Our planet balances liquid water, a protective atmosphere, a steady magnetic field, and a climate that stays within life-friendly bounds. Shift any one of those too far: thinner air, weaker field, tighter or wider orbit, and a world can swing toward a frozen desert or a runaway greenhouse. These details make another Earth rare by definition and push scientists to be precise about what habitable means. The simple guide is the habitable zone, the orbital band where surface water can stay liquid, but temperature alone is not enough. Real habitability depends on a planet's makeup, the thickness and chemistry of its air, the elements available at the surface and in the oceans, and the stability of the host star. A planet can sit in the right band and still fail if flares strip its air, or if greenhouse gases trap too much heat. Over the past decade and a half, the hunt for such worlds moved from idea to measurement. Space surveys found thousands of exoplanets, some rocky, some puffy, some in tight orbits that scorch, others far out and cold. Each discovery sharpened the filters used to find the few that might resemble home. Super-Earths tempt with the promise of thick air on rocky ground. Gas giants teach how often big planets form and how they sculpt smaller neighbors. Distance sets a hard limit. Many known exoplanets sit hundreds or thousands of light years away. Interstellar travel to those reaches is not realistic for now, which is why the nearest systems matter most. Only a world that is not just temperate on paper, but truly hospitable, could justify the time, risk, and cost of a crossing measured in decades. Alpha Centauri sits at the front of that queue. Two sun-like stars share the system, with Proxima, a dim red dwarf, drifting farther out. In the mid-2010 seconds, astronomers reported an Earth-sized planet in Proxima's temperate zone. Its closeness electrified the field, but the host star is active. Flares and high-energy radiation can chip away at air and water unless the planet's magnetic field and atmosphere are strong. Even with those challenges, the find pushed hard, practical, talk about how to study the nearest systems in detail before sending anything across. Barnard's star, about 6 light-years away, is another strong target. It is relatively quiet for a red dwarf and close enough for high-precision monitoring. Evidence points to a cold super-Earth in a months-long orbit. Such a world would likely be frozen at the surface, yet could still hold subsurface water if interior heat is high. Careful measurements, minute stellar wobbles, and faint dips in starlight keep refining these hints and clearing false alarms. Finding a planet is only step one. Next comes reading its air and climate from far away. When a planet transits, a thin strand of starlight filters through its atmosphere. That light carries chemical fingerprints, water vapor, carbon dioxide, methane that hint at surface conditions. But chemistry can mislead. Venus holds plenty of carbon dioxide, yet burns under a crushing sky. Mars shows ice and ancient riverbeds, yet lacks the air and shielding life needs at scale. These contrasts keep scientists cautious about labeling any distant planet another Earth based on 1 or 2 molecules alone. Why push so hard? Partly for safety. History reminds us that a single world can be fragile. Impacts, supereruptions, climate swings, and our own choices can stress both planet and people. Spreading out reduces that risk, but exploration is also part of who we are. The stars offer questions we cannot answer from here about life, geology, climate, and the range of possible worlds. Reaching for them expands both knowledge and perspective. The distances are daunting. At current speeds, a ship would need thousands of centuries to reach the nearest star. That reality has pushed engineers to study new propulsion, nuclear thermal and nuclear electric engines for higher efficiency, fusion concepts for higher exhaust speeds, and light sails pushed by lasers for tiny, fast probes. Each approach trades one limit for another: energy, mass, heat, precision, and each demands patient testing in deep space. A suitable destination remains the hinge. Without water, air, and accessible resources, a crossing becomes a long cruise to nowhere. Artificial habitats help, but long-term settlement works best with local rock, soil, sunlight, and ice. Terraforming far-off worlds is worth modeling, but is not a near-term tool. For now, the right plan is to find planets that already sit close to what we know works. New instruments speed that search. All-sky surveys map transits across bright, nearby stars and feed targets to larger telescopes. High-contrast imagers and sensitive spectrographs then split faint light into clues about air and clouds. Space observatories add reach, cooler optics, longer wavelengths, and the stability to stare for hours. Together, these tools move us from counting planets to reading them. Even with better targets, time remains long. The first interstellar missions will likely be robotic and multi-generational in spirit, with teams handing off work across decades. That raises practical and ethical questions. Who flies? Who decides? How crews or autonomous systems govern themselves far from Earth, and how culture and education persist in a sealed, distant environment. A starship would need rules that value continuity, health, and care for both people and machines. Host stars change, which matters for planning. Some brighten with age. Many red dwarfs erupt more when young. Sun-like stars are steadier but shorter lived. A target world may be welcoming now, but less so in the far future, or the reverse. Picking a destination means thinking on timescales longer than any mission we have flown. The search unites many fields. Astrophysicists model orbits and climates. Chemists and biologists study pathways that could leave telltale gases in a planet's air. Engineers design shields, power systems, and guidance that can last for decades. Ethicists and policymakers weigh rights and risks for travelers and for any worlds we might touch. The work is broad because the goal is broad, not just to find water, but to show that a place could hold the full range of human life. Building places to live in space instead of searching endlessly for a second Earth is an idea that grows stronger the more we learn about the universe. Planets with the right mix of air, water, gravity, and climate are rare. Nearest stars are still light years away. Alpha Centauri sits more than 4 light years distant, so even light needs years to arrive. With current propulsion, a ship would take tens of thousands of years. Against those facts, constructing habitats we can fully control starts to look less like fantasy and more like a practical path for growth and safety. Humans adapt. We have made homes in deserts, on coasts, and in polar cold by shaping shelter, water, and food to our needs. The same logic applies to space. If a natural planet will not meet our limits, we can design controlled environments where pressure, temperature, air mix, lighting, and even gravity are tuned for human health. Concepts span rotating stations that make gravity by spin to pressurized domes on moons and asteroids. Designs focus on shielding from radiation and micrometeoroids, keeping heat and air inside, and letting the crew work, grow food, and rest in a stable, daily rhythm. Early visions came from Konstantin Tsiolkovsky, who imagined rotating cylinders that produce artificial gravity. Mid-century studies by Gerard K. O'Neill expanded those ideas into giant cylinders and tori large enough for farms, lakes, and towns. These O'Neill cylinders place mirrors around the structure to bring in sunlight, set day-night cycles, and support soil, trees, and water systems. Because they could be built in Earth or lunar orbit, inspection and resupply would be simpler than crossing to a distant world. Designed worlds offer options nature rarely does. Weather can be mild and predictable. Air can stay clean. Crops can grow year-round under controlled light and water. Gravity zones could vary by module to study health or support rehab. Parks and rivers would be planned for both biology and well-being, blending natural forms with careful engineering. In these spaces, the environment adapts to people, not the other way around. Radiation is a serious hazard beyond Earth's magnetic field. Habitats answer it by putting mass between people and space. Thick walls, water layers, packed regolith, or magnetic shielding to divert charged particles. Materials research may add new composites that block radiation without adding too much weight. With proper design, dose rates can be held to safe levels for long stays. Sourcing materials is another key. Launching everything from Earth is expensive. Lunar regolith can become shielding. Asteroids can supply metals, rock, water, ice, and carbon. Sunlight is the main power source. Mirrors and concentrators feed solar arrays and thermal systems. Closed-loop life support recycles water, air, and nutrients. Waste becomes input for bioreactors and soil. The goal is a system where losses are small and most matter cycles over and over. Such habitats also push us to rethink world. A world need not be a sphere with plate tectonics and deep sky. It can be a cluster of modules with tailored ecosystems, forests in one ring, kelp farms in another, labs and schools nearby, all tuned to the same safe air and gentle climate. Modules can be swapped, upgraded, and extended. If more room is needed, build another cylinder and link it to the network. Scalability is a central advantage. While Earth-like planets are scarce, the number of buildable habitats is limited mostly by resources and skill. Life in these places would shape culture. People would grow up with stars always in view, with careful use of water and power a normal part of life. Art and music would echo the hum of machinery and the curve of rotating horizons. Communities would depend on cooperation. If one part fails, all help repair it. Governance would focus on maintenance, health, education, and fair resource use. Looking outward each day could deepen care for the larger cosmos and for the fragile, shared systems that keep everyone alive. Habitats become stepping stones. Once we know how to live off Earth at scale, these places can serve as depots, shipyards, and research hubs. Crews can test propulsion, long-duration life support, and radiation countermeasures without the delay and risk of planetary travel. A network of stations in cislunar space, at Lagrange points, and along inner solar system routes would support exploration farther out. The same network also acts as a safety net. If Earth suffers a crisis, people, knowledge, and industry continue elsewhere. The engineering challenges are large, but not mythical. Robotics and teleoperations can do heavy work in vacuum. 3D printing and in situ resource use cut launch mass. Inflatable and rigid modules can be combined. Autonomy handles routine checks. Humans focus on planning and repair. Agencies and companies are already testing pieces. Inflatable habitats, closed-loop air and water, precision assembly, and refueling in orbit. Each demo slides another block into place. Artificial worlds also offer relief for Earth. Population and demand grow. Habitats can add new living space without paving forests or draining rivers. Agriculture in controlled environments can reduce land and water stress. Energy drawn from the sun and space can be steady and strong. These sites can serve as test beds for recycling, indoor farming, and waste-to-resource tech, with results that feed back to Earth. Health is central. Living with reduced gravity harms muscle, bone, and circulation. Rotating habitats answer by setting spin and radius to target Earth-like acceleration. Daily activity and exercise can be designed into layout and routine. Medical care adapts to low radiation, clean air conditions, tuned diet, and lighting that supports sleep cycles. Green areas, varied spaces, and social design protect mental health. Alongside habitats, one more idea helps bridge the distances between stars, slowing or pausing biology for the trip. Travel times to even the nearest stars are so long that crews would spend much of a life in transit. Cryogenic sleep and suspended animation, imagine a pause button. Cool the body to slow metabolism, or put it into a protective state that halts most biological activity, then revive at destination. Medicine already uses cooling to protect the brain and heart after injury. Therapeutic hypothermia lowers temperature to reduce oxygen demand and slow damage. That is far from decades-long stasis, but it shows that slowing the body can help. Cryogenic sleep pushes to much lower temperatures, near the 196 degrees Celsius of liquid nitrogen. To prevent ice crystals that tear cells, cryoprotectants replace water in tissues enter a glass-like state called vitrification. In theory, a vitrified body could sit unchanged for long periods and be warmed and revived later. Suspended animation may not need such extreme cold. It aims to switch on natural pause modes, like those seen in animals, to slow life safely. Nature offers hints. Tardigrades survive drying and freezing by entering cryptobiosis. Some frogs freeze solid in winter and revive in spring. In trauma rooms, induced hypothermia buys time for surgery. These cases do not solve human long-term stasis, but they prove that biology can pause and restart under stress. If cryosleep or a milder suspended state can be made safe, mission design changes. A ship could cruise for decades while its crew sleeps, waking near a target with no subjective time lost. That avoids the heavy psychological and social load of multi-decade confinement. It reduces life support demand during cruise and simplifies habitat volume on the ship. It also turns a difficult generational mission into a single crew mission. The hurdles are significant. Freezing an entire human without damage, keeping tissues stable for years, and then warming evenly so organs and vessels function is beyond current practice. Brains must retain memory and identity. Metabolism must restart cleanly. Even if the biology works, ethics and law must answer hard questions. A sleeping person cannot consent day to day. Who makes decisions for them? What rights and protections apply over decades of stasis? Research points to possible tools. Better cryoprotectants reduce toxicity in ice formation. Nanotechnology or microrobots could monitor and repair tissue damage at a small scale during stasis. Smart materials might control warming rates from core to skin. Artificial intelligence can supervise life support, navigation, and fault response while human oversight is paused. None of this is routine today, but each piece is under study for medicine, space systems, or both. Taken together, habitats and stasis sketch a practical arc. We do not need to find a perfect twin of Earth to begin living beyond it. We can build controlled, shielded, scalable homes in nearby space and learn how to keep people healthy there for years. From that base, we test propulsion and autonomy, send small probes to nearby stars, and refine radiation shields and closed-loop systems. If suspended animation becomes safe, crude interstellar missions shrink from an unsolved epic to a hard, bounded engineering problem. If it does not, habitats still deliver more room for life, cushions for Earth, and the practice needed to thrive away from a planet's cradle. The work asks for patience and cooperation. It blends astronomy, ecology, medicine, materials, robotics, and policy. It treats space not as a distant stage for a chosen few, but as a nearby workshop where we can build, study, and share. With careful design, clear safety margins, and steady testing, artificial habitats can turn the empty dark into places of light, water, and growth. And if we can also learn to pause the human clock for a time, the long road between stars becomes less forbidding, one careful step at a time.